Hi everyone, today we have a problem based on SHM, simple harmonic motion. And in the scenario today, we'll be talking about a diatomic molecule, which means we'll be talking about a two-particle system. So, in this case today, we are to find the time period of this entire two-particle system. So in order to figure out the time period, we'll have to figure out the value of omega, since the time period is 2 pi over omega. We know that omega is equals to root of k over m for any problem in SHM. But since we do not have k here, we'll be using the Taylor's method of SHM here in this question. So what Taylor's method is basically this k can be written as the derivative of the force function over the mass, and the mass has to be taken as the effective mass of the entire system. Now, the effective mass or the value for mu for the reduced bodies will be m1 m2 over m1 plus m2. This is also known as the reduced mass of this entire system. Now, in order to find the omega, we'll not be finding the omega for the oscillations between the two molecules. Rather, we'll be keeping this body m1 at rest and finding the oscillations for this particle m2, right? Which will be the omega for our scenario. So, we know that fx for any SHM problem is equals to kx, and the derivative of this force will be equal to k, the fact we used over here. This method is known as Taylor's method, right? So we'll be solving our problem today with the Taylor's method. Now, the omega will be the root of f dash x over the reduced mass we calculated above. In order to find the force, we are already given with the expression of the potential energy, and since we know that the force is just the derivative of this function, and getting the modulus to be on the safer side so that a negative sign does not create complications later in the square root. So the derivative of this will be 2b times r minus r naught. So now we have the force as the function of x. In our case, this x is r, which is the distance between the two particles of the diatomic molecule. So we have 2b times r minus r naught as f of r. Again, we'll be derivating this with respect to r because we are to plug in this value over here in the final expression of omega. So this derivative comes out to be 2b. Now, we'll be plugging in this value and the value for the reduced mass. So omega comes out to be the root of 2b divided by the reduced mass, and the answer will be m1 plus m2 over m1 m2. This will be the value for omega, and hence the time period can be evaluated further. So that was one way to approach this two-particle problem using the Taylor's method, which again is a very handy and very easy method when it comes to solving problems of SHM, right? So that was it in today's video, and thank you so much for your time.